Yesterday, as I said, I was quite enthused by the level and quality and the quantity of the questions. So there were some comments which I actually didn't want to make on the very first day, thinking that it is a bit advanced. But then I find that you have been lapping it up. So I inserted a slide in order to make those comments because they are important, but I was just wondering whether to make it or not. So this is related to this process and the metric which we wrote down here. Now I want you to take a moment and actually appreciate what we have achieved. This was on the first lecture within some 15 minutes or something. You started with the principle that you can write down the amplitude for different histories for a particle which is propagating, and then we argued that this amplitude has to be of the form e to the I theta. Then if the path has small bits, it has to be additive, therefore we said it has to be the length of the path. This length of the path immediately tells you that you now know how to write down the propagator for a particle to move from one event to another in the presence of an arbitrary external gravitational field, however strong. Because the length of the path in an arbitrarily strong gravitational field is known to you, just from this Green's function, for example, you can obtain black hole evaporation. So first lecture 15 minutes over, we have put quantum mechanics and gravity together, GAB and H cross, and you get that result. And in fact, I will derive it in some way like this later on. And it comes with enormous economy of effort, which is what I want you to appreciate. The principles which we have used is almost logical, and you can obtain this result. The second point, this is something which somebody asked yesterday. See, we wanted this thing to be linear in the length, that is, should be like dxa. So that is why we said it is like square root of some object and it is linear in length. There is another way to get linear in length. That is to take dxi or dxj and multiply it by some vector aj. That will also be linear. Then you can integrate it from one point to another. This is just some constant. Just like you put m here, you put q here. Okay? So now you have extended the action, you have written down one linear object, then you have written down another linear object, and then you can work with this. It will turn out that this aj is just the vector potential, 4 vector potential in electromagnetism, and the two classical fields you ever knew, namely gravity and electromagnetism, straight comes out of this principle that the path of a particle moving in some arbitrary space-time has to have a linear terms like this and this. So there is one more comment which I will just throw at you and leave because I don't have time to discuss it. You might ask, if you are going to take GAB and put this and put a square root, why not put an MA, B, C, D, put 4 of them and put a 4th root, or n of them and take an nth root. If you put 3, it runs into some problems with parity and things like that, but as long as it is even number, it is fine. This is some issue which some of us have been working on in some unpublished manner, but this is an open question. If anyone is interested, let me know. Then there is one more comment I wanted to make. This is also of advanced nature. I thought somebody might ask, but nobody did. This has to do with the form of this action which we wrote down. Now think of a free particle. Then it is 1 minus v square by c square square root dt. Now this is for every path, and then you are going to sum over all the paths. So a given path's velocity can be much higher than c. This is all the paths you are drawing and you are computing it. So then square root of 1 minus v square by c square is going to become imaginary. So what do we do with that? What do we do with those paths? You do nothing, you just sum over them also. Now there are two ways of thinking about it. One way of thinking about this is that if I have a event in space-time and I draw my light cone here, classically a particle can only go inside the light cone. It need not be straight line, but it can only travel like this. It cannot go from here to here, it cannot propagate like this because it will need speed greater than that of velocity of light. But if you are bringing in quantum mechanics into special relativity, it is possible that something which is forbidden classically is allowed quantum mechanically. It is like tunneling, and whenever there is a tunneling, the amplitudes come down exponentially. So the I factor in square root of 1 minus v square, you can say, is just damping it. This is one way of thinking about it. but it will turn out as we go along that this problem really doesn't arise. When you do it properly, you will only get positive definite numbers, and we will come back to it. There are some subtle issues related to that, and in fact, a rigorous mathematician will tell you that any path you can draw on the blackboard contributes a set of zero measure in a path integral. So, the paths which contribute into path integrals are what is known as fractal paths. Anything which you can smoothly draw on a blackboard is set of zero measure. So, even that has to be taken into account, and as I said, this is a subtlety. It does not affect anything practically. So, I just wanted to mention it to you. We will come back to it at some stage. Okay, now let us get on with what I have to talk today. So, we went yesterday up to this point. Then I said, so we have got the non-relativistic action, and we had even written down the propagator's Fourier transform expression, but we do not know f. So, the question is, how do we compute the propagator? We will first do it for the non-relativistic particle. There is a general result which I need, because everything which I am describing here we are going to require when we get on with more advanced aspects in gravity. Whenever the action is quadratic in its variable, that is, it has q dot square, for example, or it has q dot, or it has q square, things which has only two q's, so to speak. And if it is quadratic, then there is a very simple way of computing the path integral. What you do is the following. In the path integral, you are supposed to sum over all paths q of t between two endpoints. You first take the path which is extremizing the action, call it a classical path. So, you call this qc of t, and then whatever remains you call it, let us say, mu of t. This is a fixed quantity between the two endpoints. So, summing over all q of t is same as summing over all mu of t, because this is fixed. Now, if you compute the action for q, if the action is quadratic, then it will split into action for qc plus action for mu. There will be no cross term. Why is there no cross term? That is because the classical path is something which is extremizing the action. So, any linear deviation from it will not change the action. Therefore, it will get into this form. This is independent of mu, and this is where we are summing over the mu. But interestingly, this mu has to vanish at the endpoints, because all these paths q of t has a fixed endpoint, q1 t1 to q2 t2, and the classical path also has the endpoint values q1 t1 and q2 t2. Therefore, mu will be 0 at t1 and 0 at t2, right. That means that when I am doing this sum over all paths, this q here is my mu here, and this is A evaluated for the classical path, which just comes out of the summation. So, you are doing this sum. Of course, this is a sum which I have not even defined. I have not even told you what this funny symbol means, what is sum over path mean. But whatever it is, once you have done it, it is going to only depend on t1 and t2, because there is no q dependence there. Therefore, you immediately get the result that the propagator for any quadratic action is some function of t1 and t2 multiplied by exponential I of the classical action. That is, you evaluate the action along the classical path, and this is all you get. So, now it is trivial. Let's take free particle for example. For free particle, you compute this action. That is easy, because free particle has constant velocity. So, x dot square is a constant, you integrate. So, it is x square by t, right. So, here t stands for the time difference and x stands for the spatial location difference. And somebody asked in yesterday's this thing whether what about the spatial translation invariant, that is what is coming in. This x stands for x2 minus x1, t stands for t2 minus t1, and this n is some extra n of t. But how do we determine n? That is where the transitivity kicks in. We sort of said that the action, the propagator has to satisfy this transitivity condition. You use that in this form, and you will find that the action is naturally transitive, but it will give you a condition on this n. You put that thing in, and if you work out the integral, you will find that this n of t is m divided by 2 pi I t in d dimension, d spatial dimensions, d by 2. Okay. So, you can already see that I am not giving you the details of the derivation. This is completely straightforward, trivial, and it is also available in every textbook in path integrals. Okay. So, if you are serious and you haven't seen it before, you should work it out. It is easy to work it out. The easiest thing to do is to take this, plug it into the transitivity condition and make sure that it satisfies it. I mean, it's not really deriving it, but you at least check for consistency that this is your propagator. So, you have got the propagator for a free particle. This is our first example. A second example which we will need is simple harmonic oscillator. So, simple harmonic oscillator, if you calculate the action for an oscillator to go from Q initial to Q final in a time interval 0 to capital T, and the oscillator's frequency is omega, this is what you will get. How do you derive this? You know the oscillator equation of motion, the solution is A cos omega t plus B sin omega t. Then you plug in the initial condition that at t is equal to Ti, it is at Qi, and t is equal to Tf, it is at Qf, that will fix your A and B. So, you know the trajectory. Go and plug it into half m q dot square minus half m omega square q square, integrate, you will get the classical action, and this is the result. Okay. Again, these are textbook results and I do not want to spend time on that, and you should work that out if you do not know, and it is available in every textbook. So, use the transitivity again to fix the constant in front, and you will find that the constant in front is given by this object. Okay. So, we have evaluated the first two propagators in non-relativistic mechanics. Okay. Now, okay, this is the final answer, which this prefactor and this action, the classical action thrown in. We will need all these things, so that is why I am just quoting it for you, and you do not have to write it down, but you should roughly know that this is the kind of form it has. There is one more issue I want to take up here, which sometimes confuses people. The propagator which we have been talking about, we started with a wave function and multiplied by the propagator, integrated to the space coordinate, and said the propagator propagates the wave function forward. What happens in Heisenberg picture? So, in Heisenberg picture, the state vectors do not change. I am assuming everybody knows a little bit of quantum mechanics, but the operators evolve, and the operators evolve by this rule. If they, I will use a Hamiltonian which is independent of time. So, closed system. So, this is the Hamiltonian, and the operator at time t is operator at 0 with these two things sandwiching on the both sides. Okay. Now, usually you take the operator at 0 to be the equal to the Schrodinger operator, but that is not really needed for us. So, this is the way in which operators evolve in Heisenberg picture. Now, I am going to define the eigenket of the operator at time t with an eigenvalue A by this relation. So, the operator at time t is different from an operator at time t prime. Therefore, I should know which operator I am using, that is this t label. Then its eigenvalue will tell me which eigenket I am choosing, that is this A label. Now, you can rewrite this by taking this A of t from this, and you will find e to the h t this part and e to the minus h t times t A, this is the equation you get. Now, what that means is that this quantity acting on this object, which is this, is you take this quantity to the left, it is A into e to the minus h t. Now, of course, you find that this is some ket and this is another ket, and A acting on 0 gives you this. Therefore, that quantity is just the eigenket at t is equal to 0, which means that this object T A is this quantity e to the minus I s t multiplying the eigenket here. Just make sure you understand that. So, this entire thing is eigenket at t is equal to 0. Why? Because this is the eigenvalue equation for A of 0 acting on this gives you A times this quantity, right. Therefore, it is the eigenket at t is equal to 0. So, because it is an eigenket at t is equal to 0, I can take this and call this quantity and take this to this side and write this equation. So, the eigenket at time t is e to the h t times eigenket at 0. Wow, interesting. Remember, this is Heisenberg picture. States do not evolve in time. So, this is not a time evolution of a state in spite of these labels, and in fact, e to the h t comes with the wrong sign, and it is just, as I said, a confusing notation. Okay. These are all eigenkets defined by eigenvalues of the operator at different times. And by convention, when it is evaluated at 0, we will drop it and just call it A. But this is something which is useful. It is useful, for example, to write down the propagator. In fact, for any observable, I can say that the eigenket at T A and T prime A prime is this is e to the ist 0 A and e to the minus ist 0 prime A prime. So, you take these two together and e to the minus ih T prime minus T, and the eigenkets at T is equal to 0 are just usually denoted by convention without any time label. So, this transition element is the evolution operator sandwiched between the two eigenkets at T is equal to 0. In particular, if you take the position operator, which evolves in time in Heisenberg picture like any other operator evolves in time, if you take T1 x1 to T2 x2, which is our propagator, that has an equivalent representation in this form. So, you do not need path integrals and things like that, you can work in terms of Heisenberg picture, and in Heisenberg picture this is the result. And there is, you can also compute the actual value of this using this, but this is an interesting way to look at it. For us it is useful because I can now take this formula and insert a complete set of energy bases here and here. So, what I mean to say is that I have this quantity e to the minus I h, assume we are, okay, I will write it exactly as it is there, T2 and T1, and then I have this x1 here, you introduce an energy eigenket En here, then you put a En here, and you put here a Em, and you put a Em here and an x2 here, and you sum over your m and n. Okay. This is exactly the same as that. This expression here is same as this expression because I just introduced a complete set of energy eigenkets. What is this? This is just the wave function in energy representation. This is what you call the standard eigenfunctions of the Hamiltonian. So, that is phi n of x1 star because it comes in the other direction, and then you have a phi n of x2. This is more of a convention, what you call star and what you do not call star. So, you put these two, but this quantity e to the minus ih T2 minus T1 acting on E1 En will give you an En here because that is the eigenvalue of the Hamiltonian operator, and then En Em will give you a Dirac delta function or a Kronecker delta function in the discrete case. So, you just get a sum over this. This is again important because what it is telling you is that there is yet another way of computing the propagator. So, the first way to compute the propagator is to actually sum the paths. Nobody ever does that because we do not know how to do it for an arbitrary action. Quadratic, yes, but non-quadratic we have no clue. Second method of computing the propagator is to take this e to the minus IS2 and sandwiching between these two. That sometimes works, sometimes does not work because you may not be able to compute it. But if you can solve the Schrodinger equation for energy eigenvalues, which is a classic differential equation approach, then you know what these guys are, then you can write down the sum. Now, this is probably the most practical method, but then you will have to evaluate a sum, and that sometimes works and sometimes does not work. So, the way to compute propagator, I have given you 3 different methods. And this is going to be very, very useful to us. So, given the energy eigenfunctions, you can do this and vice versa. Okay? Fine. Now, I want to make another comment which is somewhat of an advanced nature, which has to again to do with the form of the action which we have introduced. So, the action which we have introduced is of a very standard form. You start with a Lagrangian which depends on q and q dot, and you put delta q is equal to 0 at the end points, and then you get the equation of motion. So, because you are setting the variation of q at end points, that is q is sort of fixed at the end point, I put a subscript q here, and you get a particular differential equation. Now, it turns out that you can also introduce an action or Lagrangian which will give you exactly the same equations of motion, but with delta p set at the endpoint T1 and T2. That is, instead of fixing the coordinates, you are fixing the momentum. that action is just this action LQ minus d by dt of this quantity, dl by dq dot time, this is just p, so it is pq, you subtract. Now, how do I prove that this is going to give the same equation of motion? It is almost a look-see proof, but if you do not believe me, work it out. When you vary the standard Lagrangian, what happens? In the end, you are going to get a p delta q at the end points. Now, if I have added a pq here and I do a d by dt, when I integrate, it is going to give me a q delta p and a p delta q, one of them will cancel out. You will have a q delta p hanging around. If you put delta p is equal to 0 there, you will get the same thing. But am I not just adding a time derivative to the Lagrangian, and haven't you taught somewhere that if you add a total time derivative to a Lagrangian, nothing will happen? So, the equation of motion has to be here. Why am I making such a big deal? It is a big deal because first of all, that statement that if you add a time derivative to a Lagrangian, the equations of motion does not change is applicable only if it is a time derivative of a function of q and t. No q dot is allowed to appear there. Here we have a p here which depends on q dot. So, that theorem simply does not hold here. Second, that theorem tells you that if you add a total time derivative, then when you vary the action keeping delta q0 at the end point, you get the same equations of motion. That is not what we are doing here. We have changed what are the fixed at the boundary conditions, and so you can write down a momentum space Lagrangian from the coordinate space Lagrangian. The reason I brought this out again is that you won't see it in textbooks, but there is a nice path integral representation for that. What happens is that in quantum mechanics, given this amplitude for a particle to go from q1 to q2 in a time interval, you can ask what is the amplitude for the particle to go from a momentum p1 to a momentum p2 at time t1 and t2. Now, the general principles of quantum mechanics tells you that what happens in momentum space is the Fourier transform of what happens in the coordinate space. So, given this, if you take a Fourier transform in q2 and q1, introducing the conjugate variable p1 and p2, then you get that propagator. So, what you have to do is to take the standard action, which is exponential of this, sum over paths. You are doing a Fourier transform. So, there is a I times p2 q2 minus p1 q1, and there is an integral over dq1 and dq2 in order to do a Fourier transform on this. But this you can rewrite because p2 q2 minus p1 q1 is just d by dt of pq at the end points. So, what you have got left with is that essentially you take this integration over q1 and q2 into the measure on this path, because the path itself is a whole lot of integrations on the coordinates. You also integrate over the endpoint coordinates. So, you have left with this LQ minus d by dt of PQ. If you work it out, this whole thing, this LP has this beautiful feature that it depends on second derivatives of Q. Again, that shatters the myth that there is the usual comment that if the Lagrangian contains second derivatives of Q, then the equations of motion should contain third derivatives of Q. Okay? No, it is not. This is a case where the equations of motion are still second order in time. That is because it has a very special structure, and we are also fixing delta p at the end point. The reason I spend all these, because the sort of topic of the lecture series is quantum theory and gravity. So, this is the quantum theory part, and the gravity part is that the gravitational Lagrangian, which we know has this structure, but this is just an example that if you start with the standard Lagrangian and you do this, the momentum space Lagrangian will have a q double dot minus half q dot. This you can immediately work it out. So, this I wrote down to explicitly show you that it will have a q double dot term, and it will be linear in that q double dot term. You cannot get this by just removing a total time derivative of a function which depends only on q and t. You cannot do that. So, you will get this expression, and as I said, this is the structure of the Einstein Lagrangian. Now, this is advanced, and this slide is intended for those who know a little bit about GR. So, in general relativity, the action which you take for gravity is something called a Ricci scalar root minus j d4x. Now, it turns out that Ricci scalar contains second derivatives of the metric tensor. It is exactly like what I wrote down here. This is your dynamical variable, your metric tensor, you will have the second derivatives of that. but this Lagrangian is linear in that second derivatives. So the Ricci scalar is also linear in that second derivatives. So you can actually write it as a bulk term and a surface term. What happens is that this surface term which you have added here is actually has the same structure as PQ. This is the Lagrangian. Take the derivative of that with respect to Q dot. Of course, you do not take Q dot in relativity, you take all the derivatives and then you multiply by Q. So this is like PQ structure, and it is just that it carries more indices, but this is the surface term, and from this surface term you can actually obtain the bulk term. So that is why I called it holography, in the sense that there is a talk between the surface and the bulk. So there is fair amount of work which has been done by me and collaborators on this, but there are still a lot of open questions here. For one thing, nobody understands, and understands in the entire course refers to what I said yesterday, that nobody can tell you immediately that, oh, gravitational Lagrangian should have this structure. Okay? If you work it out, it does come through, but there is no simple qualitative interpretation as to why it is so. It does get that interpretation if you approach gravity as a thermodynamic system. There is a way to relate this as a free energy, entropy and the energy, and E minus Ts structure will fall out of it. So what you think you are extremizing an action, you are actually extremizing the free energy of a system. So this is yet another reason to think of gravity as a thermodynamic system. But other than that, there is no explanation for that, and it is an interesting project to think about. Okay. Now I want to get on with more tools which we need for doing quantum field theory. We are almost getting there. And I want to make what could be slightly provocative statement, but I would like to be proved wrong. Path integrals are like many things which you know, which are extraordinarily elegant and beautiful and completely useless. We all know examples of that. So there is not a single problem in physics I know of which can be solved by path integrals, but cannot be solved by any other method. I know a lot of problems in physics which can be solved by other methods and simply cannot be solved by the path integrals. So that proves my claim. Of course, path integrals are far more elegant than any other approach you know for quantizing a system. I love it, okay? But it is just a love for elegance, not for utility. This situation dramatically changes when you bring in what is known as a Euclidean time. So there is a preface to that. All that I have said so far is the normal path integrals in normal time and space. So I want to introduce something called a Euclidean analytic continuation of time. And when you do that and you view path integrals in that so-called Euclideanized space, it sort of gets a life of its own, and there are lots of insightful things you can say there, which is enormously difficult to obtain by other methods. It just falls out and you cannot get it from the other method. So in fact, the path integral approach and the Euclidean time goes hand in hand together. They sort of supplement each other very well, and that is what I want to introduce next. So the idea is basically simple. In the path integral, you have e to the I times some quantity and you are summing over that, or you are going to integrate over that. Now, integrating something like e to the I x square, for example, is a tricky business because this thing does not really converge. But if only I can make e to the I x square into e to the minus x square, well and good, because it converges at both ends and I can integrate. So is there some way of converting the action in such a way that the action can become a negative semi-definite object, that is e to the IA. We want it to become e to the minus something which is positive definite. Okay? There is a very simple trick to that. So let us illustrate it in standard classical mechanics. So you have this quantity, I times A is what I want in the path integral. So what I am going to do is to analytically continue from real t to imaginary t and call IT as TE. To be precise, what we are doing here is something like this. You have, let us say this is your standard beloved real t, and this is the imaginary t which we are introducing as a hypothetical construct. So what we are talking about is that you have a theta here and you take t e to the I theta and change this theta from 0 to pi by 2. So this sort of rotates and sits here. Okay. So this is known as some Euclidean rotation or Wick rotation or analytic continuation or any of these words. But by and large, this is the simple algebraic statement of that. So if you do that, this dt, I times dt is going to become dte, no minus sign yet, but this is going to give you a minus sign because the I is there, and this already has a minus sign. So you pull out a minus sign, and this is for any potential which is bounded from below, which you can set to 0. This is a positive semi-definite quantity, which means I can do everything which I have done in the normal quantum mechanics in this Euclidean time sector. So in particular, if I have been using the signature minus dt square plus dx square plus dy square plus dz square, when I change dt to I dt, it becomes dt square plus dx square. So that is a Euclidean 4-dimensional space compared to a pseudo-Riemannian 4-dimensional space. That is why we call it Euclidean. So what we have is a Euclidean propagator, which is again sum over paths of this kind. And for example, if you look at the corresponding free particle propagator, it will be minus half mx square dt square, and there is no I factor, it is a real quantity. Okay. Now, having said that, you should realize that the paths which we are summing over, this funny symbol is for sum over paths. The paths which we are summing over in the Euclidean sector are very different from the paths which we are summing over in the normal sector. For example, if I have a path, let us say x is equal to t square. Then if I put t is equal to it, very nice, it becomes x is equal to minus t square. But tomorrow I will give you a path which is x is equal to t cubed. Now if you put t is equal to I, then that path is not even real. I want the paths to be real. So we are going to sum over here all paths x of t which are real. So all the paths, the set of all paths in the Lorentzian case, that is when it is t and time and space are different, and the Euclidean case where time and space are treated in more in consonance with each other, the class of these paths are very different, but the things magically work themselves out and you get the correct results. And in fact, in one of my papers, I have titled a section as the unreasonable effectiveness of Euclidean continuation. We really don't know how it works, but it works, and you will see several examples of that. And as I said, along with action principle, it is an extraordinarily powerful tool. And without this, action principle is a bit lame. I mean, that is what I try to convince you in the beginning. Let us go a bit further. Let us have some practical uses of that. So the first one is that take this Euclidean propagator and write it in that expansion which we worked out here. But now the it has become a nice e to the minus en te, and we have a Hamiltonian which is bounded from below, so I can take this en to be sort of nicely ordered, and there is a ground state E0 and E1, E2, E3, etc. Now suppose I take the limit, so it is a closed system, so it is going from 0 to some t, and suppose I take the infinite time limit, t going to infinity. What will happen to this sum? Of course, if you put t equal to infinity, the whole thing will go to 0, but we don't do that. You take the asymptotic behavior. When t is very large, this is going to suppress everything except the most dominant term will be the one where En is the smallest, which is the ground state energy. So the asymptotic form of this will be just the ground state wave function times E0 of t. This is very good, because if I know the propagator, I just take t is equal to ite, and then you take this limit, then I get the ground state wave function and the ground state energy. And in several condensed matter examples, etc., people would like to know what is the ground state of the system or the ground state energy of the system, and it will follow. Of course, you need some method of computing this propagator without, of course, solving for the Schrodinger equation, in which case you don't need that. But in many cases, you can do that by WKB approximations, etc. You have a question? Yeah. That is correct. Except that all ground state wave functions are real. This is the theorem. Okay? So it's good that you pointed it out. It should be phi naught star. I could have put phi naught star, but it wouldn't have made. That is right. I'm assuming ground state is non-degenerate. Okay? So otherwise, if, to be precise, you will put it, but you will see that these things just go away in a moment. But what we are going to do next, and here is where it goes away. If you want to get the ground state, ground state energy, then all you have to do is to take a logarithm. When you take the logarithm, you will also get a log of psi naught and psi naught star or whatever. But I am going to divide by t and take t going to large limit, and only the other quantity will contribute, and that will give you E naught. Okay, so the ground state energy you can compute by this process. And most importantly, something which we are going to use extensively, in fact, to give probably the most beautiful derivation of the thermal effect in accelerated frames, is that you can also get the ground state wave function of a system from this quantity. What do you do for that? So, you take this Euclidean W x1 to x2 at time t, and you divide it by assuming x1 is 0 and x2 is 0. So, both of them has e to the minus e naught t hanging around, that will cancel out. So, you will have phi naught of x2, phi naught of x1 and phi naught of 0, phi naught of 0, okay, or with a star, it does not matter. Now, if I further put this variable x2 to 0 and call x1 as x, you will have one of them here, let us say x2, which we have put to 0, so that will cancel out. You get phi naught of x divided by phi naught of 0. Everything here is a constant except this phi naught of x, and the constant can be fixed by normalizing phi naught, so we do not care. Therefore, you get the result that the ground state wave function of a system is the limit t goes to infinity of this quantity. It is proportional to, but we do not care because the proportionality can be fixed by normalizing. Yeah. Oh, W was defined here, so I can tell you that again. W is that the defined as the t going to infinity limit of this. Okay. Okay. So, because W is that just what you were asking, t going to infinity of this, and G has a path integral representation, you can write the ground state wave functional as a path integral. This is important, committee to memory. When you want a ground state wave functional of a system, all you need is the Euclidean action of the system with a particular boundary condition. And what is the boundary condition? You are of course going to sum over all paths, but the paths are going to start at t is equal to 0 at some point x, and it is going, when t goes to infinity, that path is going to go to 0, the coordinate value 0. And this is summed over and it is separated from the boundary conditions with a semicolon. So, this object gives you the ground state wave function. So, if you know the action for this system and you can Euclideanize this system, the path integral will immediately give you the ground state wave function. And this again will turn out to be very, very powerful, and that is a nice way to do things. This whole thing, I told you that this Euclidean time has a life of its own, and already I had hinted at that something interesting is going to happen when you do this quantum field theory and gravity, and there is going to be thermodynamics, etc. And when these approaches come together, there is a unique relation between what is called the thermal density matrix and these path integrals in the Euclidean plane. So, I want to derive that next, because as I said, these are all bits and pieces of tools which you are going to require, and that is what I am doing here. So, what is a thermal density matrix? In case you haven't come across that before, it is a very elementary object. Suppose you have some object, some observable which is built out of Q, quantum mechanics. So, this is some observable, it could be Q to the power 4 for example, or sin Q, or it could be even, it can even have other variables, but for simplicity I am just taking an observable built out of Q alone. And I want its expectation value in a given energy state. So, that is easy, you take the energy eigenfunction psi n and psi n star and you integrate over dq. So, this much of this will give you the expectation value of this operator in the nth energy state. Then I come around and say, well, actually I do not know which energy state it is. It is actually in thermodynamic equilibrium at temperature T. Therefore, the probability that it is in energy state En is e to the minus beta En, okay, with some normalization factor here. So, if it is in that energy state En, then this is the expectation value, but the probability for it to be in that is e to the minus beta En. So, I have to sum over all n in order to take an average over thermal and quantum. So, the thermal plus quantum average of this system is given by this expression. But this expression can be written in a slightly nicer way. What you can do is that you have this O of Q written here, this is Schrodinger picture, and Q is just a multiplicative variable, and then rest of the quantity which is integral and the sum I define as a rho QQ, where I have defined a quantity rho Q Q prime, as the psi n at q, psi n star at q prime, e to the minus beta E n and summed over all n. Okay. Now, make sure that you understand that this gives you this, because now if I put q is equal to q prime and then I take this O of q, so that is going to give you the probability which is obtained by this integral. This is psi n of q and psi n star of q is just mod psi square, that is what you will get here. Then there is a e to the minus beta E n which is put here, and then you are integrating over dq. Okay. So, this quantity is known as a density matrix, and in quantum mechanics the most general description of a quantum system is in terms of a density matrix, but I will not go into that. But this is for our purpose definition of a thermal density matrix for a system defined by some Hamiltonian for which these are the eigenfunctions. But what is interesting is that, remember this formula we wrote on some time back, if I can get it. Look at, okay, they look at this formula and now come back to this formula, keeping that in mind. They look almost identical. All that I have done is, if I have put IT here, you would have got that. Therefore, you get the result that the thermal density matrix is just the Euclidean propagator to go from q prime to q in a time interval 0 to beta. So, beta, which was inverse temperature, is now turning out to be the imaginary time coordinate. Remember that this beta, just to stress that home, this beta came from thermodynamics, while in the Green's function or the propagator, this beta came from a time variable, but the time was Euclideanized. So, it is the Euclidean time. Okay. So, you have a Euclidean time beta for going from here to here and 0 to beta, that gives you a thermal density matrix. Now, just think about one more thing. We found that when you are computing averages, you are going to do trace of this quantity. Trace means just you multiply and you equate the variables and integrate over q, but this is the formal way in which people will write that, and you want to normalize it with trace of rho. So, when you are taking traces, you are going to put q is equal to q prime. So, what does this mean? What it means is that a particle is starting at a point q at time t is equal to 0, and it is coming back to the same point q when time is beta. And if I just keep repeating it, you can conclude that it is periodic in the imaginary time. So, if a system is periodic in imaginary time, it will mimic thermality. So, if you have a quantum system where by some independent argument you can show that your propagator is going to be periodic in imaginary time, then without any other extra work, you can say that the propagator will describe a thermal distribution and the temperature you can read off from that period. Roughly speaking, if you want to just need a take home message, it comes because e to the minus Th is what you use in quantum mechanics, and e to the minus beta h is what you use in thermodynamics, and this Th is what we have called the imaginary time, and that is what comes. Okay. This is basically it. I mean, this is a bit of an oversimplification. You can think of it as a mnemonic device, and that is how the periodicity in the imaginary time kicks in and gives you this. This is, as I said, is over simplifying a very beautiful result known as KMS condition in thermal equilibrium, etc., etc. But for our purpose, this is good enough. Okay. Now, this thermal density matrix, I want to give you an example, and the example which we will need is that of a harmonic oscillator. So, you take the harmonic oscillator's Euclidean propagator. So, you first add the harmonic oscillator's normal propagator, then you put t is equal to it. So, every sin theta will become I sin h of theta, and every cos theta will become cos h of theta, and then there is this normalization factor and an exponential. This is just your sin h. If I take it outside, this is what we had before. The sin became sin h, cos became cos h, and this is the expression. Okay. This you can obtain from the standard simple harmonic oscillator's propagator, which we have written down. I am just using this principle. You take the propagator and put this beta and 0. Now, with a little bit of trigonometric ingenuity, you can rewrite it in this form. You should just write it. It's some +2 level trigonometry. So, you can write this sin h and cos h in a different form. Then you get a nicely symmetric thing with a q minus q prime the whole square times a cot and q plus q prime the whole square times a tan h. With this beta omega would have become beta omega by 2. This is an expression which we will need fairly later on in one of the lectures. So, this gives you the thermal density matrix of a system. Conversely, if you have a system which has a density matrix which has this form with nice cot and tan coming like this, then I can read off the temperature of that system like this. This is how we will, this will be yet another proof of thermality when we come to accelerating frames, etc. Fine. So, this is all sort of preliminaries for results which I am going to need later on, and we have been delving in non-relativistic quantum mechanics, but we are supposed to do field theory, which means we have to do the relativistic quantum mechanics, which means I have to calculate the relativistic propagator, not the non-relativistic propagator. So, how do you compute the relativistic propagator? Well, we had the expression for the relativistic propagator, I am sure it is written down there. It is sum over paths e to the minus I times mass times the length of the path between the 2 points. So, I had to just sum this quantity. This length is a square root of something, which means that I can't use that nice result for quadratic actions. It is not a quadratic action, so I can't use that. Now, I can't use some of the other nice results like what happens with the transitivity. The relativistic propagator will not be transitive in time. That is obvious if you think about it, because relativistic propagator treats space and coordinate time at the same footing. Nobody told you that the non-relativistic propagator is transitive in space. Therefore, relativistic propagator by that token will not be transitive in time. You cannot sum over paths up to a point. You can't write down a relativistic wave function. That is why there is no Schrodinger equation for a relativistic body. Well, there are other reasons, like for example, if you take, let us take an electron and a positron and keep them to be very, very low energy, almost zero velocity. So, they are non-relativistic. You have a non-relativistic electron and a non-relativistic positron, and you nicely write down a Schrodinger equation for this two particle system. After some time, they annihilate each other and you do not know what you are talking about, and you do not know what Schrodinger equation to write. When particle numbers change and the particle characters change, Schrodinger equation falls on its face. So, that approach is banned for us. But propagators will still live. They will outlive this crisis. But you have to compute the propagator. Now, it turns out that there is a perfectly rigorous way of computing this object, which I am not going to describe to you because it is fairly technical. Technical meaning it is complicated technical, but you can read about it in my QFT book. But I just want to mention it to you because I am going to get you the same result by a more heuristic approach, which is very nice, very physical, but it is not completely rigorous, and I will explain to you where the lack of rigor comes in. Okay? But before that, let me tell you, if you are looking for rigor, the way to do this is the following. We already know how to do things in the Euclidean plane. So, you first take the relativistic this IML and you go for the Euclidean vector of that. So, the square root of 1 minus v square by c square, which came from dt minus dt square plus dx square, will become dt square plus dx square. So, it is a nice good length in a Euclidean space time that is always positive semi-definite. That is why I told you don't worry too much about that minus sign and the square root, because the way we are going to give meaning to that propagator is in the Euclidean sector. So, there everything is fine, and the I also will disappear by the same reason that dt will give you that extra I factor. So, you will have something like this. So, now you have a Euclidean space, and this is the length of a path connecting one point to another, and the path is parameterized by some parameter s, let us say, and then you have to sum over all the paths. What you do is to introduce a lattice. So, you do something like this. Let me do it in 2 dimension. So, you introduce a grid, let us say a square lattice, and you say that a particle is propagating from here to here by different paths. So, what are the paths now? One path could be this, another path could be this, etc. So, you count how many paths are there of a given length L, okay? Then you multiply each one of them by e to the minus ml and you sum over. But this is in a lattice. Finally, you want to take a continuum. So, you have to take, if the lattice spacing is epsilon, you have to take that epsilon going to 0 limit, and you have to do that carefully, and that is where all the technical part and the regularization etc. comes in. The way you define this quantity is that you first define the propagator in a lattice, this is in the lattice, and instead of mass you introduce some quantity mu which will take its mass's place, which depends on the lattice spacing, and then you also multiply it by some measure m of epsilon based on this epsilon, and then finally you take epsilon going to 0 limit. So, you have to specify these quantities in order to give definition for the path, and once you do that, you can write down this expression which I told you. This is, you take a path whose length is n, capital N, in lattice spacings. So, it is n epsilon. So, the length here is n times epsilon. Instead of m, you multiply it by some mu of epsilon. This is the number of paths of that length connecting origin to a point r here, let us say. Okay? So, you need to know how many paths are there in a lattice which goes from square lattice or a cubic lattice, which goes from one point, from the origin to a point r with a length L. That's a beautiful problem in combinatorics, so I won't spoil the fun by telling you, work it out. But it is there in my book, but try to work it out. It's a nice combinatorics problem. This can be written down. There is an explicit closed expression for it. And in fact, the sum can be done in an explicit closed form. Rather, it is simpler to take its Fourier transform with respect to this R. Remember that R is a d-dimensional vector, and that quantity can be written down in an explicit closed form. Then you can take the limit, work the whole thing out, and you will get this result. You will find that the Euclidean propagator, now we have, this is a great point in the moment in our evolution over the last 2 hours or something. We wanted to find the propagator for a relativistic particle to go from one point to another, and we have it here. That is given by from 0 to some point x, where this x is a d plus 1 dimensional vector. It is a Fourier transform of a very simple expression, p square plus m square Fourier transform. Okay? If you, this is in Euclidean sector, and then you have to rotate it analytically back. If you do that, you will find that everything works through this p square plus m square, this p square has a p0 square plus vector p square, and that sign will flip when you go from Euclidean to Lorentzian. So, it will become p square minus m square. Now, there is a slight problem. The problem is that when you integrate this along any of the p axis, the denominator is positive definite. So, it never vanishes. So, you do not cut a pole in the real line. But if this I epsilon was not there, you have a p square minus m square. When you integrate over p, there will be a pole, and you need to know how to avoid the pole. That is where I have put this I epsilon. It is not something which I put. If you do this and you rotate it back, you will find that this is what you need. So, let me spend a moment explain this to you, because this may be new to many of you, but actually it is a very simple concept. So, in order to illustrate that concept, let me take a harmonic oscillator, ordinary harmonic oscillator. So, the harmonic oscillator is d square by dt square plus omega square, and I want to write down its Green's function. So, this is the definition of a Green's function equation. This is the Green's function, this is the Dirac delta function in time. Now, the standard way to do this kind of a problem is to Fourier transform the equation. So, from G you go to some G of nu, which is the Fourier transform of this G. Then when you do the Fourier transform, this is going to become just minus nu square. So, you will get minus nu square plus omega square times this G of nu, and the Fourier transform of Dirac delta function is 1. There are 2 pi factors all over the place, but do not worry about them. So, this tells you that G of nu is 1 over omega square minus nu square. Okay. This minus nu square comes from this. So, if you want a Green's function g of t, that is another Fourier transform back something like e to the minus I nu t dt minus infinity to plus infinity. So, we have solved the problem. Yeah? Sorry. D nu. Okay? So, we have solved the problem. Of course not. This integral does not exist. Okay? This integral says integrate over nu along the real line, and when nu hits omega, it blows up. So, it does not exist. But now comes the trick. Suppose I had done this in the Euclidean time, then dt square would have become minus this quantity, and if I went through the whole thing here, I would have got one extra minus sign, so it would have become this. This is well defined, and in fact, it is an inverse, it is a Laplace transform of a Lorentzian, it is exponential, right. So, you can immediately work this out in the Euclidean, and the result you will get is, because it is exponential, it will be e to the minus omega modulus of t, omega is positive. Sorry? It won't, because the Fourier transforms both in the Euclidean sector and in the other one is always taken with respect to this. This will be TE, but I won't touch this I. So, you independently define Fourier transform in both these spaces. Since it is an important point, let me spend a moment on that. You have the Euclidean equation for the Green's function defined by this. Now, you Fourier transform it. After writing down the equation, you do the standard Fourier transform and then get it back. You do not write down the Fourier transform in the other case and then change I to ET. That will be the purpose. This is a Fourier transform, it is never a Laplace transform. Okay? So, you do Fourier transform both in Euclidean sector and in the main curve. Thanks for bringing it out, this can be a confusing issue. Fourier transform is just a technique. So, you use it with TE in one case and T in another case, and you get back this. Okay? So, this is the result which you get. What does this mean? This means it is theta of t e to the, okay, if you again cut, okay, this is GE, so let me leave it there. And then if I am going to go into G of t, you will pick up this I factor, this I should again put a E here. So, that will become theta of t e to the minus I omega t plus theta of minus t e to the I omega t. This modulus translates into e to the minus I omega t going forward in time, this is minus t, and e to the, if you think of this as a positive frequencies go forward in time and negative frequencies go backward in time. This is the function which you will get if you do it in Euclidean and continue back. Now, you ask the question, okay, I do not want to do Euclidean. So, I want to live with my original integral. So, my original integral was g of t with a minus sign here. Okay. Now, can I give a prescription so that I get the same result? Because the result is defined in the Euclidean sector, but I do not want to go to Euclidean sector and come back. How do I do that? Okay, you take a look at it. Where are the poles? The poles are in the, this is real of nu, this is imaginary of nu. The poles are at omega and minus omega, and you are supposed to go along this. So, in how many ways you can avoid the pole? One way to avoid the pole is that you can go up like this, go up like this. This is good. Then depending on the sign of t, if you close the contour like this, you will get a 0. If you close the contour like this, you will pick up both of them. This is known as the retarded and advanced propagators for the Green's function. On the other hand, you can also do something else. You can sort of close this contour here and close this contour here. Then you will get what we have done there. But what does this mean? What this means is, remember that this is the contour which is doing this, which is equivalent to just pushing this here and pushing this here and keeping the contour along the real line. I mean that is exactly what that I epsilon is going to do for you. How do I see this? There is a very simple way. Suppose you are doing the integral along this. Complex function theory tells you that I can just rotate it like this, because everything is analytic there. The poles are sitting here and there. I won't touch it. I can't rotate like this. I will hit the pole. But if I rotate it like this, I can take this to this, take this to this, and I can take the integral along this. That is exactly what we did when we did the analytic continuation to the imaginator. Therefore, if I have defined the theory on this and I rotate it back, it tells you that I should avoid one pole below and one pole above. It will tell you exactly what to do, and that is what this I epsilon is going to do. Okay? Now, these are standard stuff, but since some of you might not have come across of that, I am spending a moment on that, and you will read more about it, for example, in my QFT book. I mean, this is completely well known, how to go from here to here, etc. Okay. So, we have actually got the propagator if you have done the sum, but I haven't done the sum for you, so I will derive it for you from a different way. That different way is interesting because it introduces something known as Jacobi action, which you usually do not come to know of. It is a very beautiful concept. What we are going to do is to translate the known path integral, which is quadratic, to another path integral which involves a square root. So, we will prove an equivalence. Then we will say that if I have a square root path integral, I can convert it into a quadratic path integral, which I know how to do, and that is what we will do. So, the Jacobi, in order to introduce the Jacobi action, let us start with the kinetic energy, which is essentially dl by d lambda the whole square. Lambda is like time and L is the length, and the length now I am going to write as some g alpha beta x alpha dot x beta dot. Dots denote derivative with respect to lambda, and x alpha of lambda is a path, let us say, in space time or whatever. This is, I am going to now do this entirely in space. So, I am going to use the convention that English letters A, B, C, D, I, J, K, L, M is 0 to 0, 1, 2, 3, and Greek alphabets alpha, beta, gamma, delta is going to go over spatial coordinate. This is what is known as the, but different books use different convention. One reason to use this is that when you are writing papers, you will be typing 4-dimensional indices more often than 3-dimensional indices, and English letters are easier to type. Okay? So, it is an economical thing to use. So, this is g alpha beta dx alpha dx beta dot, and in particular, for example, you may be talking about a particle which is moving on the surface of a sphere. So, this g alpha beta will be the metric on the surface of a sphere. Okay? So, you can write down this kinetic energy. Then I look at the action, which is just kinetic energy minus potential energy, and I rewrite it in a slightly different way. Since Hamiltonian is p q dot minus L, the Lagrangian can be written as p q dot minus h, which is p alpha x alpha dot minus h. Nothing new so far, this is standard stuff, just rewritten. If I vary this, I will get not the path of the particle, I will get the history of the particle. So, I told you in the very first day that one should have two different nomenclatures, one for path and one for history. So, when you solve the action, you get x as a function of t, y as a function of t, z as a function of t. But you might say, look, I do not want to know that. What I want to know, for example, it is whether the planets are going around the sun in elliptical orbits or hyperbolic orbits. I do not care where the planet is at a given time. So, if you only want the path but not the history, then it is possible to write down another action, and that is called as Jacobi action, actually Maupertuis Jacobi action. A lot of people have contributed to it. It works best for systems where h is a constant. So, if h is a constant and if it is a closed system, then one might as well say that when you are varying, I do not have to worry about h, and I can just look at this part. So, that is, there is the motivation. You look at an action principle where action is just p alpha dx alpha, is p dq, integrated from one point to another, where this p should be now written as a function of the potential v and the energy E which we have frozen. If you go and vary this action, what you will get is a path in space. There is no time information here at all, because it is just dx alpha. So, if I put a d by dt and dt, then that dt and dt I can change it into any other function. It is reparameterization invariant. It only gives you the spatial information. So, what is this? This is dl by dx alpha dot x alpha dot. Now, you can do a little bit of transformation with it. So, I have x alpha dot dl by dx alpha dot, and L is a quadratic of second order. Yes, you have a question? No, this is classical mechanics, you do not sum over anything. This is Jacobi action for a classical particle. We are not summing anything. A given energy E, you tell me one energy today, another energy tomorrow, I will give you the path for each one of them. Okay. So, we will sum over the energies when we do quantum mechanics, we have to. But in classical physics, that energy is a fixed quantity. Okay. So, this quantity is just twice T because it is a homogeneous function of degree 2, which is just m dl by d lambda square, but that for a fixed energy is just 2E into E minus V of x. Therefore, this m dl square by d lambda square times d lambda, you can write it as m dl by d lambda times d lambda, it is just algebra, and you convert for this dl by d lambda from this, you will get a 1 over square root of m, and then there is an m here that will take it here, and you get this. Now, you can easily understand that this is just p. E minus V is p square by 2m, that multiplied by 2m is p square root of that is p dl. Okay. But the important point is not all these long expression in square root, but dl. Now, you have got an action which has integration over L. For example, if you think of a free particle, V is 0, E is a constant, so I can take it out, and a free particle actually moves from one point to another, minimizing the length even in classical mechanics. That is of course true, trivially true, it is a straight line path. Okay, so, this dl is what we are after, because dl intrinsically has a square root in it. Where is it? We define dl somewhere. Yes, dl intrinsically has a square root over this quantity. So, if I can do the path integral with a Jacobi action, then I can construct how to do path integrals with a square root action. That is what we want for a relativistic particle. So, how do you do a path integral with a Jacobi action? Well, you can't, but you can translate Jacobi action result to the other action result, because there I know both the results. So, I get a translation table. What do? I say that, look, suppose I have the standard action principle where I go from 0 to t x1 to x2. I could have thought of it for a system with a conserved Hamiltonian, that I first go along different paths x1 to x2 with a Jacobi action with an energy E, and then you do what he was saying, that you sum over all the energies. But when you are summing over all the energies, quantum mechanics tells you that you have to put a phase e to the minus iet, because the amplitude for a particle to propagate with an energy E has a weightage e to the minus iet. So, this you convert just for convenience into integrals. So, you take this and you integrate over dE. You assume that system is bounded from below, so that you can do a 0 to infinity integral, and then you have a summation of this action. So, if you know this action, then you can get this action, because it is just a Fourier transform. I mean, you can put it from minus, if you are scared about doing a Fourier transform with 0 to infinity, think of it as minus infinity plus infinity with a theta function inside. So, what you know is that this Jacobi action path integral, which is what we want, because Jacobi action has a square root, we want to know how to do path integrals with a square root. So, a path integral with a square root action is given by the normal path integral, which we all love and we know how to compute, with a Fourier transform e to the iet integrated. Here also I can put 0 to t rather than minus infinity plus infinity, because these kernels are defined with the theta function. Okay. So, they will take care of themselves, it does not really matter. So, if I know the propagator, and if I do dt e to the it dt, that will give you the probability for going from here to here. Now, this is enormously complicated way of finally obtaining a very simple result. If you know a particle is propagating from one point to another, and you want to know what is the amplitude for it to propagate with the energy E, then quantum mechanics tells you that you kick in this phase and integrate over t. So, this is the probability for a particle to propagate from x1 to x2, not in a time interval, but with an energy E. But that is exactly what is given by the Jacobi action, because Jacobi action gives you paths with a fixed energy. So, if you just write down this, that should be equal to this. and this in turn is going to be equal to this, so you just do a Fourier transform. Okay? So I just went through the mathematics to tell you that this is how it comes about. Therefore, now you take a system with V is equal to 0 and a constant E, of course. Then the sum over e to the I root 2m L, this is the important thing. Now we know how to compute, oh I have rubbed it out. We know how to compute e to the I length of the path actions summed over all paths by doing a thing where it is the square and this is quadratic, and that quadratic actions I know how to sum. So this path integral which I know, then by taking a Fourier transform I can compute this path integral. So what we are going to do for our particular case, now come back to the relativistic propagator, one honest computation in this lecture course, where you are trying to, not completely honest, but almost honest computation in this lecture course, to calculate the relativistic propagator for a system from the action itself. So what you do is you start with the action, this action is this, which is eta AB dxa dxv. Eta AB is 1 minus 1 minus 1 minus 1. So I have put it as eta AB xa dot xv dot, where this is some parameter lambda, it does not matter what parameter you are using. So the relativistic propagator is a sum over this, and that sum has this square root action. Now you go back and write down a correspondence. We already have this result, which I have just reproduced it for your convenience. So what I am going to do is to put E is equal to m by 2. E is just a parameter, I am going to put it equal to m by 2. It is just an algebraic result which we are quoting, no physical significance here. So if you put m by 2 here, 2 will cancel out, m square, square root of that will give me m. So I have got e to the minus I m L here. Then on the right hand side, the GAB is this diagonal object. So this L is nothing but this quantity. So that is obtained by this path integral and then an extra integration over time. But what is this path integral? This path integral has 1 minus 1 minus 1 minus 1. It is all quadratic. Therefore, I know the result. The result is essentially exponential minus mx square by time half, because this is the path integral for a free particle. But remember, x square now is t square minus mod x square. Okay? So the only place where it kicks in is that when we wrote down the expression for the action for a free particle, I put a d by 2 here. For every dimension contributes a m over 2 pi I tau. Okay? So if there are 4 dimensions, I should have got a 2, because d by 2 will give you 2. But if you do it correctly, you will get an extra I factor. Not that it is very, well, it is actually important. You get an extra I factor because one of them is going to come with a negative sign. So you have the quadratic integrals where it is t dot square minus x dot square. If all of them was positive, then everything would have been fine. Since one of them is flipping the sign in one place, instead of I, you will get a minus I, and when you take a square root, you will get an I. So you work this out. So this quantity is the amplitude for a relativistic particle. It has a simple physical meaning. To go from an event x1 to an event x2, when the clock it is carrying is showing a proper time tau. That is very, very similar to your standard free particle propagator in non-relativistic quantum mechanics, because the structure is identical. The only difference is that this is not what you are going to observe. What you are going to observe is after you have integrated it over this quantity with E set equal to m by 2. So the actual propagator you want to find, this sum is given by this expression which I have derived, multiplied by e to the minus I m by 2 tau. The I m by 2 tau is just this e tau. Remember that we have put E is equal to m by 2 in order to get the left hand side right. So this sum over a non-quadratic path integral can actually be obtained as this quantity. Now you do a little bit of cleanup. The cleanup is essentially sort of scaling the variables, etc. And once you do that, the final answer is an integral with e to the minus m square mu and an exponential of x square by 4 mu. So what we have done is that you have rescaled. I don't want this m hanging around here, so you scale that out. You take s as m times some mu, so this m cancels out. You take s as m times mu, that makes it m square mu, and then ds by ds square will just give you an extra factor m. In all these calculations, there is a normalization constant in the measure which we do not know. You can set it to anything you like, but people before us has defined the propagator in a particular way, and they have set it in taking this 2 cm to be equal to unity, so that m factor disappears from that as well, and you write this as the propagator after this sort of gardening is over. There are two comments I want to make about it. First, the integral in this goes from 0 to infinity, and you want to ensure convergence. So, you put a minus I epsilon inside this, so that is minus and minus becomes plus, I into I becomes minus. So, you have a e to the minus epsilon mu, and that ensures that there is a convergence at upper bound. Okay. If necessary for convergence in lower bound, you also put an I epsilon in this, but I just thought I will show you this m square minus I epsilon here, because it will come in when we do further things with it. What about this integral? You can actually do it. If m is 0, it is trivial to do that. You will get 1 upon x square plus I epsilon. That you should try out. If m is not 0, this happens to be what is known as a McDonald function, but it is a known function. Every property about that is known. Like sin theta. Sin theta is a symbol for an unknown function. So, in the same way, there is a McDonald function, and you can write it down. And you can do that, but that is not very revealing. What is really revealing is the Fourier transform of this object, which I want to come to. But I want to make a few more comments about what we have done. What we have done here is that you are taking in the non-relativistic theory particles which go from in x and t in coordinate time, but you are only summing over paths like this. These paths cut the time axis only at one point, right? We do not take paths which go back and forth. And because of that, there is a transitivity. The transitivity of the non-relativistic propagator is closely related to this, because at any intermediate time you can say that the particle was either here or here or here, but not at more than one place. Therefore, I can integrate over that spatial coordinate along this line at an intermediate time and get the propagator to go from here to here as a propagator to go from here to here and here to here with an integration. So, the transitivity is intimately connected with what kinds of paths I am summing. In relativistic theory, you are going to take into account even paths like this. So, at a given x naught, it can be at 3 different places. We already said that. Therefore, there is no transitivity. So, the transitivity trick does not work in relativistic theories. But you can certainly draw another diagram where all the xi's are here, t, x, y, z. And then this is the proper time or the parameter along the path. In that, it is only going forward in time. This is why we did get this non-relativistic propagator here. This propagator is obtained by saying things are going forward in the proper time. As the clock which it is carrying is always going forward, it is at different places. So, in that sense, it is not very different from non-relativistic mechanics structurally, but the physical conclusions are very, very different. Okay, so these two things I wanted to explain to you. Now, with hindsight, once you know all this, you can write it down in a very simple way. You postulate that the action for a relativistic particle is not that square root of 1 minus v square by 1 minus v square into dt, but you say that the action for a relativistic particle is a quadratic in xi dot deta going from a proper time 0 to s. Then you have to stick in a coefficient which is not m by 2 but m by 4. I spent a lot of time trying to figure out whether there is a simple way to understand m by 4. Unfortunately, there isn't. You need m by 4. So, that comes from hindsight. Then you do the standard path integral. You say that this is my action. So, you say what is the amplitude for the particle to go from time 0 to proper time 0 to proper time s, from an event x1 to x2, that amplitude I have found. Then I say that look, in its own rest frame, it always has an energy mc square. Therefore, it is traveling with an energy e to the minus I ms, and I do not care about the proper time, so I integrate over all the proper time. If you do that, you get back exactly the same propagator. So, the propagator can be thought of as a particle going from one point to another in some proper time s, and then integrating it over this e to the minus I ms with this action, and you will get back exactly the same result. Okay? So, it would have been lovely if there is an interpretation for 1 by 4 and people can think about it, and if somebody finds a way, let me know. it is not easy to get by. You can't do rescaling, etc. Simple tricks don't work. You need that to get the correct propagator, and you get this result. Fine. Now I want to probe this propagator a little bit more. So two things I want to do. First, I want to take its four-dimensional Fourier transform. So you take the propagator and you take it four-dimensional Fourier transform. The propagator is 0 to infinity d mu upon mu square, this factor, and it had a e to the minus x square upon 4 mu, right? We wrote it down. Because instead of taking a Macdonald function and Fourier transforming it and looking up in a table, it is much easier to take this integral representation and doing the Fourier transform. So you have an x square here and you do a e to the ipx and you are doing a d4x. So x square has a t square, it is all quadratic, so it is all Gaussian and with an I factor, and it is a Fourier transform of a Gaussian, so you are going to get a p square essentially. So you will get a p square, and this mu, this standard deviation 1 by mu will become mu there. So you will get a mu p square term. That is very nice because that mu p square will go and sit here. And because every one of these integrals is going to produce a square root of mu, all of them together will give you a mu square which will cancel it out. So you will get essentially e to the minus I p square minus m square minus I epsilon integrated over d mu, that is this quantity. This is exactly what I told you you will find if you do it regulator in a lattice and then do a Fourier transform. Remember, in a Euclidean lattice, this p square minus m square becomes p square plus m square, and I epsilon is not needed. This is what we did here. Okay. So there are two ways of approaching it, and I told you there is a rigorous way of doing it, and this is the non-rigorous way of doing it by using this summation kind of a thing, using Jacobi action. It gives the same result. Now what is non-rigorous about it? And that gives you another open problem which is worth pursuing. The problem is, how do you define measure when you are doing this path integral with a Jacobi action? You would have thought that since you know how to compute the Jacobi action by some other trick, there is some way of translating and getting the measure, but it turns out to be much more complicated. So if you are interested, again talk to me and I will tell you. I am sure this can be done, and if you do that, it is a nice elegant way of deriving this result. But there isn't strong motivation for doing that sort of a thing because everybody knows the result and it is just an exercise in elegance. Okay? But that is where it is non-rigorous because I never define for you what is the measure by which I am computing the path integral. So I just went on and I manipulated one integral against the other and got the result. But the result is correct, and in that sense it is rigorous. But it would be nice to define the measure for that. So four-dimensional Fourier transform of this, I have told you, is going to give you this. Therefore, I can do an inverse Fourier transform and get G. That is written down here. So the G of x1, x2 is just a four-dimensional integral of p square minus m square plus I epsilon e to the minus ipx. This is the way most of the time you will learn in your quantum field theory textbooks, and if you are doing Feynman rules, etc. This is the momentum space propagator. That is very simple. While the coordinate space propagator is a Macdonald function. You can write this in a slightly nicer form because you can think of this 1 by something as integral 0 to infinity d mu e to the minus mu of that quantity, and just e to the minus lambda x integrated over dx gives you 1 by lambda. Okay. So you just write this in an exponential form. The reason you do that is you can again do a Fourier transform on this. So what you would have got here, this d mu, I can write as e to the ipx in a nice way. Remember, we wrote down a formula for a propagator which is e to the minus ith between x1 and x2 in Heisenberg picture. So I am trying to write something very similar here. What I am doing here is that this e to the ipx will come. Okay, let me give you this expression and then explain to you. Keep this d mu integral as it is. Then consider the quantity x1 to x2 of something like a Hamiltonian, which is box plus m square. Why is it a Hamiltonian? But after all, what is this Hamiltonian? It is p square by 2m plus v or something. P square by 2m, p square is del square, forget m square and things like that. So essentially it is going to have an operator del square. So in 4 dimension that becomes a box. Think of m square as some kind of a constant potential. This is put in just for convergence. So this can very well be called a Hamiltonian, it is actually called super Hamiltonian. So that quantity, when sandwiched between x1 and x2, the way you evaluate it is you put in eigenfunctions of this box, which is e to the ipx, right? Because if you have del square, it is e to the ipx with p as the gradient. I mean, any gradient will have a eigenfunction as e to the ipx. So you put an ipx here and you put a p here. So these two together will give you e to the ipx. Remember, my x's stand for x2 minus x1. So both of them will come through here, and then this particular object is nothing but this e to the minus I m square mu, which I needed, I have already incorporated into it. So this is just an amplitude for a particle to go from x1 to x2 in a time interval 0 to mu, and then I say that I do not care what time interval its proper time clock showed, and you integrate over a d mu. That is yet another nice interpretation of this G. So what I am emphasizing is that if you take just a relativistic particle and you make it go from point to point and you take its action, you can find the actual relativistic quantum field theoretic propagator, which will come from a field. So far we haven't even mentioned the word field, but I have to get the field out of this, and that is the magic. Field will pop out of this propagator. I will show you how. Yes. Yes, you can. You can write it down as that x dot square, that 1/4 action which I wrote down. From that you can derive it. Not from the square root action, because the square root action will always give you a square root kind of a term. It will give you square root of p square minus m square, and that is no good, and we want the square there. Okay. Now this is a good place to stop, and we will continue in the next lecture. So we can take questions now. Yeah. Yesterday, right. Summation. Okay. Oh yeah, the endpoint integration. Okay, fine. Yeah, that is right. Oh, that is straightforward. So let me. I don't need that for that. Let me just explain that to you. So in non-relativistic quantum mechanics, which is what we were doing there, because q and t are non-relativistic variables. So when you are computing a path integral, you take one point here and another point here, and you want to sum over all the paths like this. How do you sum over all these paths? The normal trick is you take this T1 and this T2 fixed, and you cut it down into small strips of width epsilon. Okay? Then in order to sum over all paths, you specify the value of any path at let us say this is some Tn, the value of the path at this, and you integrate over all x coordinate. This is my q, this is t. Okay? So you integrate over this, integrate over this, integrate over this, integrate over this, then you have summed over all the paths. So the summation over path symbol there actually stands for integration over all these times. All that I have done is that in normal summation over paths, you fix this and you fix this, so you don't integrate on these two. But when you go to the momentum principle, you just integrate over this one and this one as well. So that is just an extension of the measure. Right. No. In flat space time, it of course works. But even in flat space time, we are going to spend enormous amount of time as to what happens if you take a curvilinear coordinate system and you Euclidenize that time. Suppose you make a general coordinate transformation and you Euclidenize a new time, what happens? And that will again give you thermality, etc., and all that. But if you are in a curved space time, it is not guaranteed that if you are given a pseudo-Riemannian metric and you go and put t is equal to it, you are even going to get a positive definite metric.
For example, in the curve metric,
You don't have to go all the way to curve metric. If you just take de Sitter metric with e to the ht, if you change t is equal to it, it will become complex. Okay? So even in simple ordinary flat space time, Suppose I make a coordinate transformation that t goes to, let us say, t cubed, t is equal to tau cubed. So, if I analytically continue in t, or whether I analytically continue in tau, my results are strange because one of them will fix this thing, or tau to the power 4, etc. Yeah. Yeah.
What does causality translate to in Euclidean?
Interesting question. Nobody knows the answer. That is yet another major surprise. This is where I said this unreasonable effectiveness of Euclidean plane, that in the Euclidean plane there are no light cones. Okay? And in fact, this is something which will come and hit us at some stage. The surface x square minus t square equals 1. So, if you take a standard Minkowski picture, this is x, this is t, and you have x square minus t square equals 0, or these two light fronts. These are two null planes. If you Euclideanize it, this will become this. The only solution you have got is origin. So, if you go to TE and x, this is the point, this entire line mapped to this point. Okay? So, the concept of a light cone, 2 points which are separated by space-like distance, 2 points separated by time-like distance, all of them disappear. But once you do this in the Euclidean thing and you rotate it analytically back, that is the diagram I showed you. That is, if you take the path here and you rotate it back here, you will find that what you have essentially done is that when you are doing this, you are avoiding the poles in a particular way. There is one pole here and maybe another pole here. You have avoided both the poles when you are rotating it around. Okay? And the fact as to how you are avoiding the pole contains information about causality. Now, this actually happens even with a harmonic oscillator. So, some people will say that it is not so surprising, but if you are just taking a harmonic oscillator also, you have retarded solutions, advanced solutions, and a solution which has a combination of retarded and advanced, propagating positive frequency forward and negative frequency backwards, and that comes up from the Euclidean side. So, you might ask, what is so surprising? What is surprising is that for a simple harmonic oscillator with a time, there is anyway notion of causality. In order to have a causality, you need at least one space dimension and a time dimension. So, I think it is a bit of a mystery. It is not very clear why this happens, but it works out. Okay? The causal structure in the Euclidean structure can be, you can't even define it, but to the extent you understand it, it is very different from what you see in the Lorentzian plane. You have something? Yeah. Right.
Propagator is the propagator of the diffusion equation.
That's correct.
So there's something there, because causality there is also practicing the diffusion equation now as something again going outward.
Not really, because see, of course, that works only with a theta of t, in the sense that you can't change t going to minus t invariant. See, if
But that is part of the definition of the propagator.
no, what I am saying is that in the case of if you are doing it in normal quantum mechanics, it is a choice which you make. That is, if I take normal without Euclideanization, if you take the normal time quantum mechanical propagator, I can very well take t going to minus t. All that I have to do is to take I2 minus I. And it is well known that in quantum mechanics, time reversal is implemented by complex conjugation. So, everything is consistent and the system is time reversal invariant. But when you go to the Euclidean sector, you have a e to the minus mx square by tau, and you are no longer allowed to change tau to minus tau. This is not a diffusion. But this is not connected with the causality which these people are asking, because in the non-relativistic quantum mechanics there is no causality either. So, I really do not know how to merge this. There is a question of arrow of time, so to speak. Okay, that is a separate issue which is different from causality in my mind. Okay. Yeah. Okay, one of you.
So when we take t equal to iota t,
Yes.
we get the
Mm-hmm.
So if t is greater than x, that is greater than x square.
Mm-hmm.
I mean, okay, I mean the physical time. So x square plus t square becomes negative. Right?
So what?
So this.
No, I'm just looking. No, I'm just comparing two equations. X square minus t square equals 0, which has solutions x is equal to plus or minus t, and then x square plus t square equals 0, which has solutions x is equal to 0, t is equal to 0. So lines here maps to points. So, and that is just algebra. But the conclusion from that is the light cones disappear in the Euclidean sector. But that is, in fact, that was the motive behind his question. That I mean, it is only in space time that you have causality. If you have pure Euclidean space, it is almost impossible to define causality. So that is not the surprising thing. The surprising thing is I can do things in Euclidean sector, analytically continue and recover causality.
What I mean is that if 2 points are like time like separated.
In real thing, yes.
And I take t to iota t.
Right.
Then that equation doesn't have a solution because.
That is correct, but that doesn't, nobody said that all those points should have a solution in the Euclidean sector, which is exactly the point, that not only that this point goes here, these regions will just collapse into that.
So this is positive, doesn't it?
Exactly, that is what everyone is saying, that in the Euclidean plane, there is no notion of causality, because there are no notion of light cones.
No, is it no notion of causality or this space doesn't even cover the causal region?
No, there is, I mean, what do you mean by that? Once I have got this plane, it has no notion of causality. It is not that this plane has hidden some causal region or something like that. I take the Lorentzian plane and then I make an analytic continuation, I get another plane. Now, this is probably a semantic quibble. Once you have got into the Euclidean plane, people will say that there is no useful notion of causality you can define there, because there is no light cone structure. But again, I think in some sense, I think you are bothering about the wrong point. The point is not so much as to when in Euclidean sector you are losing causality. You can live with that. You can, in fact, many strong-minded quantum field theorists would say all quantum field theory should be defined in the Euclidean plane.
My worry is not this actually, what I am worrying is, I'm sorry.
Yeah, go on.
So once we make a transformation from physical time to Euclidean time.
Right.
So okay, so I can imagine it this way. I have a plane, xy plane, x and t plane, and x and t plane.
Correct.
Right, and I make a transformation.
No, there is no one-to-one correspondence. You can't just wave hand and say I am making a transformation. There is absolutely no one-to-one correspondence. For example, if I draw a hyperbola here, okay, which is some x square minus t square is equal to a square, this is going to go into a circle. No, you are disagreeing with that.
I'm not very well one-to-one because.
No, wait a minute. There is something more serious than that which is happening. This hyperbola is confined to this wedge. It never experienced a negative x value. It never went into this. This circle will go into that. Okay? So weird things will happen. So your intuition as to sort of, oh, I made a coordinate transformation is that all the coordinates in one manifold is mapped beautifully and nicely to all the coordinates in another manifold. That is not what is happening here. Okay? And in fact, what will happen is that if you take a path and it sort of goes like this for a long, long time, that path will go round and round in circles. So a path which is, single valued things will become multiply valued here. And in fact, we will see examples of that. It has physical consequences. So that is why I was saying this is not the part which worries most of us. This is fine because this is the nature of the transformation, and if you make a transformation and some regions disappear and some regions are not mapped, etc., you can live with it. Okay? But how come after doing all this, if I do physics here and I do an analytic continuation, I get the correct physics here? Well, we always thought that causality and light cone is something very fundamental to physics. And you start from an Euclidean sector which has no causality, no light cone, and you make an analytic continuation and you get the result. The surprise is that you get the correct result, not that you have lost something. You can live with something you have been lost, and actually the correct answer to this is that there are very complicated ways of doing this analytic continuation. What is usually done is one particular way. If you do it in different ways, you can recover information about all these structures. If I get time later on when we are talking about accelerated frames, etc., I will come back to that. Okay. Yeah, you heard something? Right. Yes, okay, you have to be a bit careful there because the proper time is defined only for paths which are time-like. So, if the path suddenly changes into space-like, then what you have to do is to use what is known as an affine parameter. So, if you want to physically think of a clock made from omega or whatever and he is carrying, then that is only restricted to time-like. But if you notionally think of it as a parameterization of this by an affine parameter, that works even for an curve. So, that is the right way to think about it. I keep saying time because there is a more intuitive picture. Yeah. Right. Just change of? Absolutely, that's correct. Absolutely, that is right. Because any method which you have, you can, these are techniques. So, it is like using Heisenberg picture or Schrodinger picture. Sometimes Heisenberg picture is very convenient, sometimes Schrodinger picture is very convenient. So, these three methods you should be able to adapt depending on the situation. And the Euclidean time method you will find actually brings in more physics than you would have thought of. Yeah.
And in the slide where you are taking Riemann plus quantum average.
Right.
So you integrate over dq from state q.
Right.
Observable q and then state q.
Correct.
Why not q and q prime and o to q prime?
You can, but I am thinking of the simplest possible observer I can think of.
Okay, diagonal.
No, yeah, it is diagonal in that basis. So, you just take any function of q. I told you that you can look at q square's expectation value or q to the power 4, etc. The idea was to motivate that density function. The thermal density matrix which I had defined is completely general, and that was defined with q and q prime, right. Let me just go back to that. See, I could have just told you that I define a quantity called a density matrix for a system with energy eigenfunctions given by this with an energy En. I could have just given this and be done with it. But I was just motivating it by saying that if you think of a simple observer like this, in fact, I need not have even written it like that. This psi n q and psi n star q is just mod psi n square. So, this is a mod psi n square times some function of q integrated over dq. This is the most elementary average you can do in quantum mechanics, and then you do a thermal average as well. So, I was just illustrating this concept in this case. Yes? That is right. Right. Domain of? Well, whenever there are thermal phenomena involved, like what we will be talking about extensively, Euclidean sector sort of does better. Okay, that is essentially because of the correspondence I wrote between e to the minus ist and e to the beta h. Okay. Anything else? Right. Correct. T goes to infinity. Correct.
So it is like a big T, not T goes to infinity.
Yeah, that's right. It's an asymptotic expansion. I said that. I mean, if you just put that, it will vanish. So what you do is you look at the form of the expansion. Very often you write a expansion where you say something is x square plus x plus 1 plus 1 by x kind of a thing. So you are looking at very large x and then you stop at 1 by x and then there are other terms. So it is an asymptotic expansion of this quantity on the left for very large t. That is why it is not t equal to infinity, it is t slash to infinity. Yeah. Anything else? Okay, so we are having a class tomorrow, right? Okay, fine.